Yeah, good day. Welcome to my Strength and 5 online class. Today we will be checking the stress limits on in shaft design. So under stress limits we have shear stress limit and angle of twist limit. So we're still going to use the same formula that we've learned yesterday, simple torque equation, and then as this motor is going to rotate, it means that it's going to twist this shaft. It's going to twist this shaft in this direction. So this shaft will be twisted in that manner. And then on the other side, this generator, due to, I can say, friction, or due to its mass inertia, is going to apply a resisting force in opposite direction like this. So that means this thing now is going to experience two torques in two opposite direction. Therefore, in that way, this shaft now will end up twisting. So the twisting will be like this. We expect, due to that, we expect the shaft to do this.
Divided by the length of the bar. Of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted.
So that's what we expect from that shaft as the twisting is happening. It's just that normally that deformation or that kind of movement that will happen along the outer surface. That movement will be small. You might not recognize it, but that's what is going to happen actually. Therefore, as that thing is going to happen, due to twisting, there will be deformation or the change in shape, or there will be some misalignment due to that torque. Then we have to limit that movement or that change in shape or that deformation, because if this thing moves too much from it moves from here up to there, this thing might end up breaking. So to be safe, for this shaft to be safe, not to break, then we must limit the angle of twist. So that's why we have to limit the angle of twist. The angle of twist must be to a certain value. A certain value of angle of twist must not be exceeded, because once you exceed that angle of twist, then this thing will fail, will have chances of failing. So it's not only the angle of twist that is going to be regarded as the limiting factor, as well as the shear stress. So we know that the shear stress at the outer diameter will be big, somewhere here. Therefore, this line here, this line from here to there, it represents the magnitude of the shear stress. Therefore, the shear stress as well must be limited so that our shaft won't fail. So we'll have two limits, because if the shear stress is not limited, then our shaft will be in danger of breaking. So, okay, I was looking for something here, I got it. So we must make sure that our shaft doesn't reach a certain value of shear stress. So otherwise, if our shaft reaches a certain value of shear stress, then we're going to start seeing this. We're going to start seeing one layer or one surface sliding over each other. Then in that way, that means our component will fail. Therefore, by introducing these limits, we are trying to avoid that failure, this failure that you are seeing here. This is the failure that we don't want to experience. So this is the formula that we know. We've discussed it yesterday. So I will just go straight to the question and then try to solve it. We will discuss much as we solve the problems. Right, let's check this one. We have a hollow shaft with diameter ratio 1 into 0.378. Then I can write it like this. Case number what? Case number 11. I can say 1 is bigger than the 0.378. Then it means that the big diameter will have to be the numerator. Then the small diameter will have to be denominator. So just like this. Then from there you can make a small d, the subject of the formula. You will have 0.378 capital D. Right, from there it has to transmit a power of 400 kW at blah 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 blah. From that information we can get what? The mean torque. From that information we can get the mean torque. So like this. Remember, they've given us power. Then power equals to what? P equals to 2 pi n t over 60. We do have this over 60 because our n will be in revolutions per minute. So if n is in revolutions per second, then we don't put this 60. You must be careful there. Then from here you can make t the subject of the formula, t the subject of the formula. Then you will have p by 60 over 2 pi n. Then from there you will have 400, I think it's k to the power 3 . Right, that will be the torque, the mean torque. So this is the mean torque. I spoke about it on the first lesson. So now we have to find the maximum torque. So the torque that you must use here must always be the maximum torque. Therefore, the maximum torque, I said that it will be 1 point percentage difference. So this one is percentage difference. So in this case, they said that the mean torque and the maximum torque differ by 22%. Then you will just have to put that 2 here. and then multiply by T mean. Then you will have 1.22 multiplied by T mean is 34.725. Then finally you will have 42.364 kNm. Good. So I think that is question number 1. Calculate the maximum torque transmitted by the shaft. Then question number 2 or 11.2, I think you have to edit this question. Somewhere is not right. Okay, the diameters for the shaft to exit the maximum shear stress in the shaft. It should be not to exit. Somewhere there. After shaft, you must put not to exit. So we want the diameter of the shaft or the size of the shaft that is going to result with the shear stress in that shaft not being more than 70 MPa. So the shear stress limit is given there. The shear stress limit is this. So the shaft that we're going to choose, you must make sure that when we use it, the stress that will develop in it won't be 70 MPa. Therefore, now we're going to consider the stress limit. So we can say that consider stress limit. So if you consider the stress limit, then from this torque equation, we're going to combine this and this. Then you will have Tj equals to shear stress over R. Then you will have torque, maximum torque. We calculated it already. You will have shear stress, 70 MPa. R is the radius. So always R is the outer radius. So if you have a hollow shaft like this, from here to here still R, from here to there I can say still R, from here to there still R, but here is the distance from the center to the outermost surface. Then if you have two diameters, you have to take the bigger diameter divided by 2 to get this R. We take the bigger diameter divide by 2. So for a hollow shaft, remember, you will have two diameters. Therefore, if you've got two diameters, this one and this one, this R will be from the big diameter. Right. So remember, what we are trying to do here is to find the shaft size that we can use, so that the stress that will develop in that shaft as we apply the torque won't be more than 70 MPa. So it's really up to you here how we are going to do this. It's just mathematics. But now maybe let's substitute T, maximum torque, it's 42,364 times 10 to the power 3. J is pi, hollow shaft, D4 minus this over 32, but that 32 you can put it here. equals to shear stress, which is 70 MPa over R. R, as I've said, we use the outer diameter divided by 2. That outer diameter we don't know. We'll just say capital D divided by 2. R is D divided by 2, but that 2 over 2, I'm going to put it here. It will have the same effect as I put it here. So I can put it here or there, or I can put that 32 here or there. Nothing will change. The value of this will still remain the same. Right, from there, it's just mathematics. Okay, at the stage we've got two unknowns. Now we have to reduce these two unknowns to one unknown. We're going to use this. Then where you see the small d, you're going to put this. And then at the same time, we'll be trying to solve the value of d. Let me do this. I'm going to take this thing here and then this there. And then I will have capital D over pi. Okay, I can even remove this pi. I can take this pi there. Just do it your own way. But I'm going to take this to there, and then take this to there. Then I cross multiply with this pi to there. So I'm going to have d to the power 4 minus. Remember, the small d equals to what? Equals to 0.378 capital D, all to the power 4. All to the power 4. Remember that. Equals to 70 multiplied by 10 to the power 6 multiplied by 2 multiplied by this pi. So I'm going to cross multiply with this pi, multiplied by pi over this one, 42.364 multiplied by that. Then you do your mathematics things there. Okay, I can do it with you, but I don't like doing it to save time. But let me just do it from a calculator. On this side, you can say 1 divided by d to the power 4 minus 0.378. Yeah, then you will have d over d to the power 4. That 1 point something, you can write it here, 1.02. Then that will be equals to yeah, you will have this, and then d divided by d to the power 4, you will end up having 3 there. Then finally you cross multiply with this, you take this into there, you will have d equals to, remember it's making whatever the subject of the formula here. I'm not gonna go into detail with that one since I said this mathematics. Yeah, you'll get this. D equals to 146, and then the small d will be, you get it from here, right? So that is the shaft size that we get if we don't want the stress in that shaft to be more than 70 MPa. Then we have to use this. If we apply this torque of 42.364, and then the stress that will develop in that shaft, we don't want it to be more than 70 MPa, then we have to use this shaft size. Right, from there we are done with what's that question? Is it 11.2? We are done with 11.2. Now we're going to 11.3. So what is guaranteed here is that if we use these sizes, the stress in our shaft won't be more than 70. So now on the next question, we have to consider a different limit. We have to consider what are they saying? Angle of twist. Right. First of all, as you can see there from our question, this angle is given in degrees, and then the standard unit here for calculation purposes, it has to be radians. So our angle must be in radians. So the first thing to do here is to convert that angle to radians. Then you will say theta equals to convert that 2 degrees to radians, you will say multiply by pi over 180. Pi over 180. Then you will get 0.0349 rad. So as the shaft get twisted, So to avoid failure, the angle of twist mustn't be more than that angle. So this angle here, as this thing is getting twisted, this angle here mustn't be more than 2 degrees. So it must be either 2 degrees or any angle less than 2 degrees, but it mustn't be more than 2 degrees. So once it becomes more than that, then there will be the chances of this thing breaking or failing. So to avoid that failure or that chance of failing, then we must make sure that this angle of twist doesn't become more than this or more than 2 degrees. So now we'll have to go to our torque equation like this. We're going to combine this and this, since now we're talking about the angle of twist limit. So this is the angle that we're talking about. Then you will have T J equals to G theta over L. So this is the formula that we're going to use when they say consider the angle of twist limit, then you use this. Right, so from here you can just substitute. We've got almost everything except the diameters. So we still use this very same torque, which is 42 J pi over 32. That 32 I put it here, equals to G. What is the modulus of rigidity? Is 80 GPa. No, I'm putting this thing in the wrong place. So G is here 80 times 10 to the power 9 multiplied by theta. Oh, sorry, theta is given as well. We calculated theta. Theta will be 0.0349 over L. L is the length of the shaft. So the length is what? .8. So the length is 3.8. Is this one there. So from there, it's up to you. Calculate the diameter. So just use your own math skills. Just use your own math skills here. Okay, I can try to use different way to that one that I've used before. Okay, let's multiply this by this, this by this. Then you will have 3.8 by 42.364 equals to this by this pi. A small d, remember small d equals to this. small d equals what? 0.378 d. All this to the power 4 is this part here. So I just took this part to there, then it's going to find 80 there. 10 to the power 9 multiplied by 0.0349. Yeah, from here you can divide this side by this, by the product of this and this. Then you'll have 3.8. Then this one minus this. Yeah, then from there you'll have d equals to this. This thing here will have to give you 5.873 multiplied by 10 to the power minus 4 divided by this. Then your d will be 0.1538 meter or 153.8 millimeter. Then from there, small d will be 0.378 d. Right. These are the dimensions for the shaft considering the angle of twist. So what does it mean? It means that if we use this dimension or a shaft of this size, we are 100% sure that the angle of twist that will develop due to applying the torque of this much, the angle of twist that will develop, it won't be more than 2 degrees. It won't be more than 2 degrees. It can be equals to 2 degrees or less. Right. So now on the next question, remember now we've got 2 sizes. We have the dimension for a solid shaft, we have the dimension for hollow shaft. So between those two dimensions, we have to use 1. So maybe I can write them down like this. When we considered the stress limit, we got these sizes. 146, and then when we considered the angle of twist, we got these dimensions. Capital D is 153.8, small d is 58.14 millimeter. Now between these two sizes, we have to use 1. We need 1 shaft, not 2 shafts. So we have to choose between this and this. But the one that we're going to choose must satisfy both conditions. So the shaft that we're going to use, as we apply torque on it, the angle of twist that will develop mustn't be more than 2 degrees, and the shear stress that will develop in that shaft mustn't be more than 70 MPa. So the shaft that we're going to select must satisfy both conditions, which states that the angle of twist mustn't be more than 2 degrees, and then shear stress mustn't be more than 70 MPa. So now, how to check which one will be the right one? So I'm going to do this. I'm not sure if for your syllabus you might have to know it in this way, but the answer will always be, okay, let's check here. Between this and this one is big. 146, 153, 153 is big. Between this and this one is big. So when you choose between this and this, the right answer will always be from the bigger dimensions, because the maximum shear stress normally will occur at the outer surface. So that's how you must check that the correct, the correct one that will satisfy both conditions. It will, between these two, it will always be the one with the bigger diameters. So the bigger the diameter, the better resistance when it comes to shearing, when it comes to shear stress. Okay, but let me do it in this way. Let's calculate the shear stress considering the stress limit. So the shear stress from this will be, if you go to that torque equation formula from this, then you make the shear stress the subject of the formula here, then you will have this T R over J. Then you substitute there, you will have 42.364 multiplied by 10 to the power 3 multiplied by R. R, I said that always you take the big diameter, divide by 2, then you'll have this 0.14653 divided by 2 multiplied by 32. This 32 is coming from this polar moment inertia. It's from this. Remember, for a hollow shaft here you will have pi capital diameter to the power 4 minus small diameter to the power 4 over 32 over 32. So this 32 is coming from there. Then you will get 70 MPa. Okay, let's calculate the shear stress considering the angle of twist. So we're going to use these dimensions. For stress limit, we've used these dimensions that we got when we considered the stress limit. So now we are still going to apply the same thing, but the only difference will be these diameters. Now here you will have 42.364 times 10 to the power 3 multiplied by R 0.1538 divided by 2 multiplied by 32 over pi 0.1538 to the power 4 minus 0.05814 to the power 4. You will get 60.54 MPa. So that means if we use this shaft having this size and then apply torque at that 42, then the stress that will develop in that shaft will be 60.54. So which is okay, as long as our stress is not more than 70, then it's fine. So if we use this size, the stress that will develop in that shaft will be 70 MPa. But remember, the bigger the stress, the higher the chances of failure. So the bigger the stress, the higher the chances of failures. Therefore, to be safe always, we need to have the lower stress in our component. So that's why if you had to choose between this and this, you must choose this one, because this one is having the lower stress. The lower the stress, the lesser the problem. But the bigger the stress, the more chances of failure or breakage. Therefore, between this size and this size, then we have to choose this. But okay, it's fine. Let's continue. Now, let's check another variable, which is the angle of twist. So we're going to calculate the angle of twist considering the dimensions that we got from the stress limit. Angle of twist considering the dimensions that we got from the angle of twist. So we want to know that what will happen in terms of the angle of twist when we use, if our shaft size is these dimensions, then we're going to calculate it in this way. Torque 42.364 multiplied by length 3.8 over J. J is this one. Is pi 146 over 32. You put it there, or multiply by G. 80 times 10 to the power 9. Then you will have what? You will have 0.0 0 Okay, I will check it with the calculator. No. You will get 0.04, 0.04538, but this will be red. So if you want to convert this thing to radians, degrees, you know what to do. You multiply it by 57.3, then you will get 2.6 degrees. So we're going to have problem here because the shaft dimensions, or the shaft that we must use, the angle of twist that will develop in that shaft mustn't be more than 2 degrees. But here, if we use this shaft of these dimensions, the angle of twist will be 2.6, which is more than 2, which is exceeding the limit now. So that automatically tells you that this one is not going to work. Okay, let's check this one. So torque is the same thing, 42.364. 3.8 is the length. J is this one. It's pi 0.1538 to the power 4 minus 0.05814 to the power 4 over 32. You put that 32 here, equals to it should be equals to 0.0349 red. When you multiply this thing by 180 over pi, you should get hopefully 2 degrees. Here you might get a different value. The value that might differ by bit. Your value might differ with this one a bit. Why? Because of these roundings. These roundings, the way you round this and this is going to affect this. So you must just be careful with the roundings. And then with those roundings, you might end up having 2.1 or 2.001. But actually, if you don't round, you should get 2 degrees, or you should get this. So if you get a different answer here, it's because of your roundings. Okay, what does this tell us? It tells us that if you use this size as your shaft, and then you apply this torque of 43.364, the shear stress that will develop in that shaft at the outer radius, at this radius, remember this is the radius, this is the point where you will be looking for stress. So we'll be looking for stress here at the outer radius. So the stress that will develop here, remember the stress varies from here to there. The stress here is less, here is big, here is big. So the stress that will be here will be 60.54. And then the angle of twist will be 2 degrees. So what are our limits? Our limit says that our stress mustn't be more than 70. It's either it becomes less than 70 or equal to 70. So it met this condition. That condition is met here because this value is less than 70. And then when it comes here, the angle of twist is either must be less than 2 degrees or equal to 2 degrees. Then these 2 degrees, it's still meeting that condition. Therefore, the right dimension that will meet both, the right dimension that will meet both conditions will be this one. Stress is less than 70. The angle of twist is equal or less than 2 degrees. But if this one is not going to work, because if you use this one, the angle of twist will be more than the limit. So that's why we're not going to use this. We're going to use this. Therefore, your answer for 11.4, you can just say 11.4. What did they state the diameters that will satisfy both conditions? Then you can just say then one of the reasons that we choose this shaft is that this shaft is going to give us the lesser stress. So this stress compared to this, or compared to that stress limit, 60 is less. So we can give the reason that this size will result with less stress. So that's why we choose this. Yeah, so that's it. Thank you.